So to start this passive design procedure, basically there are lots of estimation formula for us to estimate the performance of a plane. So using basic algebraic skills, we can solve it back to try to estimate what kind of plane is needed for a certain purpose. So when the purpose is given, um, we usually estimate what's the flight characteristic is needed, what's the payload, and what's the do we have to minimize cost. For this, and also what kind of control stability is needed. So in this grid, it's an easy estimation of what planes needed. In one case, and this code originally started when I wanted to build a FPV plane for tracking the birds. Uh, there's a I had a classmate that developed a project called Bird's Eye View in New Zealand, Bird's Eye High School. He developed a system to track the image of a bird to help bird counting for environmental research purposes, and he used the drones, and then I came up with the idea to have a plane to significantly give more range and a better resolution of image, because we have higher wing loading, and also better endurance, because fixed wing aircraft are really test proven in a lot of cases, and it's pretty reliable and cheap for the for to get a lot of payload. Also, it's fixed wing aircraft has good efficiency in cruising. So what I considered there was I first you first have to load the, let's say we first have to load the package, and then I create a normal airflow. We can I used just a simple linear estimation of lift and drag coefficient. This is not going to change by a lot, because usually when the material is constrained and the structure is constrained, the type of airflow is kind of constrained as well. You could easily get this data from here, or I just use the estimate data from here, or you can import some polar axis data from other software to estimate the CL and CD. But the only important thing here about the CL and CD is to get a cruising lift drag coefficient, and also the maximum CL to take into the next step. So this optim function give you the CLCD alpha angle of attack. I mean the angle of attack, lift and drag coefficient, and also the ratio between lift and drag on when it's most efficient, when it has least drag, and also when it has maximum lift coefficient. So this is kind of used for diving, getting up to speed. The CL max, in this case, give you more lift coefficient, is used for takeoff and landing, and this one gives you more efficiency when flying horizontally, because this requires the least thrust to weight ratio. And the second, we have a constraint analysis. Constraint analysis is not something that's specified to a certain type of aircraft. You could see constraint aircraft, constraint analysis of aircraft in different airplane designing books. For example, Snorri Gudmundson's General Aviation Aircraft Design has that, and also Daniel Raymer Daniel Raymer's aircraft design. So I'm not studying aviation. So I just read the book in an amateur way and took out some useful formula. But those formulas are not some high tech. These are just estimation, but these are very. I think these are very useful. You could see that I defined CA, like constraint list, the climbing list, vertical climbing rate, horizontal flying speed, and height. These are all in international units, so all in SI unit. So it's meter per second, and so on. Cruising speed is like height, velocity. Turn is linear velocity, height, and also the load factor. So the load factor is computed by this formula. So 15 here means it's tilting 15 degrees. You can just if you have that code, you can use this piece of code as a template to do that, or you could just use a load factor. And complete CA is like help you calculate this function is helping you calculate the kinetic energy density. The Q equals to 1/2 rho v squared. So taking off ground. Let's say the length of the runway, the height of the runway, and the factor, the friction factor, and let's complete all the CAs. Right, and then the initial constraint can be created and plotted. So the different lines of the different lines in here, each line represents one constraint. So as you see, the horizontal line is the weight to load area ratio. So the vertical axis is thrust to weight ratio. So T over W with respect to W over S. So why is it this important? This help you to select the least possible engine. So the engine with least thrust to weight ratio is usually cost the least, and also is the smallest, consumes less least fuel, and also is the usually is the cheapest and the lightest. So you could optimize that, find a point, but you can actually change the compromise a bit. So you could put a for loop. You can put for loop to iterate this and see if I change some requirement. For example, here I changed the SG, so the takeoff run length from 1 to 20, and see what's the sensitivity of the CA with respect to that. And after that trial, I determined to make my constraint like that, and because that doesn't have a lot of sensitivity, I can just slightly increase the engine size and get a much better ability to do the takeoff run. And after that, you could use that to analyze the payload. So payload means what the plane is actually carrying. It could be a camera, it could be a rescue stuff or whatever. And this payload is like, you could input the mass of the payload, the mass fraction of the payload. So how much fraction of weight is that payload using, And power draw. What's power is drawing from the plane. So we can create a weight analysis, so to see how much each component weighed and what's the fraction of that inside the plane. And this weight analysis is pretty common in developing especially electric powered small recreational drones. And also we can size the battery, because we have to approximate the energy density. So for if you want high bursting current, you usually use lithium polymer batteries. If not, if it's just low current, you could use lithium ion or other sort of batteries. And the number of cells and how much power do you want to draw from the battery. So this is a usage factor. I put it to 0.5 because I was kind of going conservative. And there's a function to let you sort out how much battery you should use, what's the capacity, what's the rate of discharge, and then you get a plane. This is function called size concept simple. And to use that function, we have to use the length of the plane as a constraint, and also the focus of the main wing. This is because sometimes when we develop small plane, there's a size constraint. So if you want to put the plane into the car, there's a size constraint and also a scale constraint if you're developing scale aircraft. So yeah, I just sketch draw a fuselage because I didn't honestly I didn't have an algorithm to run for fuselage. And boom, it's a plane. So where actually it gets the aspect ratio. So this part, plane it size concept simple, is kind of quite simplified because it's assuming more than assuming more than you should. It's like I'm picking experiment I'm picking an aspect ratio, a taper ratio, and also a sweep based on my experience on very conventional plane. You don't have to follow that. You could change a lot of default parameters, and you could make a flying wing for example, and there's no much difference between developing a plane in the conventional thing and the non-conventional thing, because the only thing you gotta figure out is how to size the tail, the wing, this stuff. Because if the payload, the weight, the thrust weight ratio, and the wing loading is determined, then the rest of the part is just aerodynamic and calculation and how you want the plane to handle. This part differ from so you actually have to decide whether to use a conventional concept like that or some fancy way you can write the function like that. But you have weight, you have lift, how much lift you should use and how much battery you should use. So this could give you a pretty good idea. If you choose to use a conventional concept, you could print this out so all the parameters in this plane is stored in this object plane init, and you can of course plot it. This is the way to plot it. And also I developed another thing. It's called the SC-simp conventional concept. So this computes the lever length of each tail surfaces and the main thing, and also the stability coefficients and a recommended neutral point for a plane, and a recommended center of gravity for the plane, and also these volume coefficient. So this one is the horizontal tail volume coefficient, this one is the vertical tail coefficient, the static margin, and a non-dimensionalized static energy. These are the level lengths, and these should give you a basic idea how the plane would handle, along with the other constraint. Okay, thank you for watching the video, and see you in the next one. See you in the next video. All right.